Hi, welcome back to the massive open online course of MAT 522. In this second video, we will learn how to solve the spring mass system. Solving a spring mass system is exactly solving a second-order linear differential equation with constant coefficient. In general, the solution to the motion of a spring at any time t is given by the function of x in terms of t equals to x of c plus x of p, where x of c is the complementary solution associated with the homogeneous equation. This solution is also known as transient solution. On the other hand, x of p is the particular solution associated with the non-homogeneous term. Now, this solution is also known as steady state of the motion. Since solving a spring mass system is exactly solving a second-order linear differential equation with constant coefficient, we recall all the steps that we have learned in Chapter 4. First, we assume that the solution has the form y equals to exponent mx. We construct the characteristic equation associated with the homogeneous part. Then we proceed to solve the characteristic equation to obtain the complementary solution x of c. If the differential equation contains non-homogeneous term, then we further finding the particular solution x of p for this non-homogeneous term via the undetermined coefficient with superposition principle. Next, we combine both the complementary and particular solutions to form the general solutions for the motion of the spring. Finally, we solve any additional problems if given, such as initial conditions of the spring mass system, etc. Now, let's look at the same example 1 from the previous video. A mass weighing 2 pounds stretch a spring by 6 inches. At time t equals to 0, the mass is released from a point 8 inches below the equilibrium position with an upward velocity of 4/3 feet per second. Find the equation of motion of the spring at any time t. Since we have modeled the second-order linear ODE of this spring mass system in the previous video, that is x double prime plus 64x equals to 0, subject to two initial conditions, x of 0 equals to positive 2/3, and x prime of 0 equals to negative 4/3. We proceed to solve them now. The second-order linear ODE, x double prime plus 64x equals to 0, and therefore the associated characteristic equation will be lambda squared plus 64 equals to 0. This is a quadratic equation. Now, solving this equation gives us a complex root, lambda equals to plus minus of 8i. And therefore, the complementary solution, x of c, is given by c1 cos of 8t plus c2 sine of 8t. Since this linear ODE does not contain any non-homogeneous term, therefore, this complementary solution will be our general solution now. Furthermore, we are given two initial conditions, x of 0 equals to 2/3 and x prime of 0 equals to negative 4/3. Again, we have the general solution, x of t is given by c1 cos of 8t plus c2 sine of 8t. We can now proceed to solve by substituting and considering the first initial condition. That is, x of 0 is given by C1 cos 0 plus C2 sine 0. This is equals to 2 over 3. From this calculation, sine 0 gives us the value 0. Cos 0 equals to 1. Simplifying it, we immediately have the value for C1 to be 2 over 3. What about the C2? To solve the constant for C2, we further considering the second initial condition given here, requiring us to find the first derivative of x. Therefore, differentiating this x function, x prime of t, gives us negative 8 c1 sine of 8t plus 8 c2 cos of 8t. Again, we substitute with the initial value 0. This gives us x prime of 0 equals to negative 8 c1 sine 0 plus 8 c2 cos of 0 equals to negative 4 over 3. Again, using the similar computations, sine 0 gives us 0, this term vanished. Cos 0 equals to 1. We have 8 c2 equals to negative 4 over 3. That is, the constant c2 will be negative 1 over 6. Finding these two constants c1 and c2, we resubstitute it into the original motion of the spring. That is, now we have x of t to be equal 2 over 3 cos of 8t minus 1 over 6 sine of 8t. This is indeed the real unique motion of the spring for this example. Now, the example number 2 from the same video can actually be solved in the similar way using the similar approach. That's it for this second video. See you in the next.